Thank you very much, Vice-Chancellor, for that very wonderful introduction. It's a great honour for me to give this 6th Kerferd Oration. There's been some very illustrious predecessors who've talked about issues that are particularly important to the community, this community in Beechworth and the Australian community as a whole. But I feel that I've got it's a particularly important job to do today, because the issue that I would like to address is a very fundamental one for our society as a whole. We in Australia now are embarked upon a process that will fundamentally change the nature of our economic base, in some ways over a century. It'll change our relationship with our land, and hopefully we'll end up transforming for the better us as Australians. At the moment, that process is in a very early stage. We're just talking about a pollution control scheme program to control carbon pollution. But as I'll try to explain to you, that I think that as time goes on, that will be seen as simply one of several foundation stones that will build a sustainable society in this country. I must admit, though, when I was asked to give the oration, I was a little bit worried. I was supposed to be talking about global warming in Beechworth in the middle of winter and convincing you all that this might be problematic, especially on a Sunday morning. But then I thought, well, perhaps there is some, I don't know, perhaps it seems reasonable that we should be talking about global warming and climate change in what used to be an insane asylum, particularly given some of the politics that's going on around the area at the moment. It certainly seemed appropriate to me at the time. But before we descend into the politics and start looking at what our country's doing, I really would like to spend a few minutes looking at the science of climate change, because I think it's very important for us to realise that the reason we're doing things like embarking on a carbon trading scheme and introducing new regulations and so forth is due to a problem that science is telling us about. And the yardstick that we'll measure our success by will be the science. So we're not doing it for economic reasons or political reasons, although, you know, from what you hear in the media, those aspects of the problem seem very important. At base, we're dealing with a problem that science has told us about. The climate problem is really, it's an air pollution problem at base, and that's the way I like to look at it. And the reason that I like to think about it as an air pollution problem is that well, for a start, humans have become quite good at dealing with pollution problems over the last 10,000 years. Ever since we settled down in the very first sort of villages in the Middle East, we've had to deal with pollution problems. And over that time, I think there's something of a hardwired response has developed in humans. Once we recognise a pollution problem for what it is, we generally act to clean it up. Now, sometimes, you know, by virtue of population increase and changing technologies, that those pollution problems can threaten to overwhelm us. But nevertheless, I think thinking about this as a pollution problem gives us a very good foundation for which to deal with it. Of course, air pollution problems are very different from many of the other pollution problems that we've dealt with. And that's because the atmosphere is a very special organ of our planet. And I'd like to just spend a couple of minutes thinking about the atmosphere, this wonderful atmosphere of ours that gives us all life, and that we relate to more intimately than almost anything else. I mean, when you think about it, can you imagine a much more intimate experience than taking a breath of air? I know some of you probably can, but it is, let me assure you, a very, very intimate experience. You're taking the atmosphere deep into our bodies and exchanging the gases within it and firing our internal engines. And that, when we breathe out, those molecules we breathe out spread almost instantly over very, very wide areas. After all, the breath that I'm expelling now speaking with you, in a couple of weeks' time, some of the molecules in that breath may be over a distant ocean or a distant continent such as South America, fertilising a forest or feeding plankton in that distant ocean. The atmosphere is extremely dynamic, and one of the corollaries of that is that the pollution, or the way that any nation deals with the atmosphere, is instantly translated to the whole world. It tells you that global warming is not a problem that any individual nation can deal with. The atmosphere is a great global commons, and we need to rise to the challenge of dealing with this atmospheric pollution as a species, not as a nation or anything else, but as a species. Very profound challenge, really, that represents to us, to our political organisation, the way we deal with each other, the way we deal with the world. And of course, the reason we need to do that is that unless we start moving to regulate the gaseous composition of the atmosphere for the benefit of all of us, we will compromise the future of our children. And if I can just take a step back there to think about that in the context of this 21st century of ours. You know, the best estimates we have of how we're doing in terms of sustainability are very, very alarming. The WWF publishes a State of the World summary every couple of years. The last one suggested that as we live today, we're using about 25% more of the resources of our planet than the planet can sustainably provide. And when you put it that way, it seems all esoteric, doesn't it? But what that really means is that we are stealing a quarter of the things that these young children who sung for us this morning will need in years to come. And the situation's only going to get worse. By mid-century, by 2050, the projections are that we'll be using about 2 planets' worth of resources, sustainably providable resources. And of course, we only have 1 planet. So unless we start dealing with these very fundamental issues of how we relate to the world as a whole, and climate change is right at the heart of that, we will, without doubt, I think, compromise the future welfare of the young people among us today. Just to return to the atmosphere. There is one, not only is the atmosphere dynamic, but there is one peculiar characteristic of the atmosphere that is absolutely critical to our understanding of both it and the climate problem. And that is that the atmosphere is a manifestation of life. I suppose if people do think about the atmosphere, they imagine somehow that the atmosphere is just a naturally, or the chemical composition of the atmosphere is just a reflection of the Earth. That's not true at all. On a living planet like ours, atmospheres and oceans are radically out of chemical balance with the rocks of our planet. You know, if you examine the atmosphere of Venus or Mars or any of the other planets we know about, they are actually in balance with the rocks. As you'd expect, they're all part of a single system. On Earth, however, life itself mediates the chemical composition of the atmosphere and the oceans to make those organs of this planet of ours optimal for life itself. And I'll come back after a little while to try to explain some more implications of that. But it is a very, very fundamentally important aspect of our planet and something we need to understand. You can think about our planet really as consisting of 3 organs. There's the rocks, and even they've been changed by life. It's quite interesting when you look at geology and think about how the mineral deposits that Australia now exploits so successfully, how did they form? Many of them formed as a result of life processes. Living organisms taking minerals out of ancient oceans and depositing them on the ocean floor. So there's the rocks, there's the oceans, and there's the atmosphere. Oceans and atmosphere are held in the current chemical composition by life. So as life changes, both oceans and atmosphere must change. And I'd argue that the atmosphere is every bit as much a manifestation of life as a bird's feather is or a cat's whisker. The difference being that, you know, a bird's feather is the manifestation of a single living organism. It's not a living thing itself, but it's a manifestation of the life of that bird. The atmosphere is a manifestation of life as a whole. Life as a whole creates the gaseous composition of the atmosphere and holds it within very, very tight constraints in ways that benefit life. Of course, as life changes, so must the gaseous composition of the atmosphere change. So it shouldn't surprise us that on a planet with 6.7 billion human beings now, who at night light up our planet with their electric lights as if it was some sort of celestial Christmas tree, it should be no surprise that we're changing the gaseous composition of the atmosphere. There's one other aspect of the atmosphere that we need to understand that is critically important, and that is the size of the atmosphere. And when we look up into the sky, it looks as if the atmosphere just goes on and on forever. And it's a natural reaction of many people to say, well, if the atmosphere really is that big, how could it be that us human beings are affecting its gaseous composition? How could we be in any meaningful way, polluting it and changing it. The key to understanding that is to carry out a bit of a thought experiment. Imagine taking the gases of the atmosphere and compressing them down about 1,000 times until they became a liquid. You can compress gas till it becomes liquid, yeah? And then comparing that volume of liquid you'd create by doing that with, say, the volume of the oceans. If you were able to do that, you'd be able to see yourself that the atmosphere is 500 times smaller than the oceans. It is by far and away the smallest of the organs of Gaia, the organs of our planet. Yeah? So, atmosphere 500 times smaller than the oceans, oceans much smaller than the rocks. And the importance of that observation is that small pollution sinks are much more readily disrupted or disturbed by a given volume of pollution than large ones. And I'd just like to illustrate that point by having a brief look at the pollution histories of the ocean and the atmosphere over the last 50 odd years. I'm 50 years old, so it's not a bad sort of round figure to pick. You know, over that time, humans have been, we haven't been sparing of polluting the ocean. You know, as my mate John Doyle keeps telling me, he said, the history of civilization is simply a history of connecting bums to the sea with sewage pipes. I mean, it's true, you know, that's what it is. 6.7 billion of us draining it right into the sea. That's what we call sanitation, you know. But not only that, we've been great at throwing all other sorts of rubbish into the oceans. After the Second World War, when the Allies captured those stockpiles of dangerous chemical weapons, vast stockpiles of dangerous chemical weapons created by the Nazis, what did they do with them? Just dumped them straight into the North Atlantic Ocean. Some of the most dangerous chemicals we've ever produced. The Russians, you know, God bless their cotton socks, I mean, over the last 30 years, they've been dumping whole nuclear reactors into the Arctic Sea without telling anyone. 17 at last count. And you think about that sort of volume of abuse that we've been heaping on the oceans, you'd think, wouldn't you, that we'd be creating some sort of global oceanic pollution crisis. Well, to date, this may change in future, but to date we have not yet produced a global oceanic pollution crisis for the simple reason that the oceans are so very large that they're relatively forgiving of the amount of pollution we put in them. The story is very different for the atmosphere, and over my lifetime I have, you know, a living memory of 3 quite separate and significant global or near global atmospheric pollution crises that are simply a result of the small size of the pollution sink that is our atmosphere. The first of those pollution crises manifested itself in the 1970s. I remember reading about acid rain in National Geographic Society magazine. And you know, what was happening was that across the Northern Hemisphere, vast areas of forest were dying. Lakes were becoming sterilised and soils were being damaged. And that was occurring because people were burning coal or fossil fuels, but particularly coal, with a very high sulphur content. And that sulphur was just going up with the flue gas and meeting moisture in the atmosphere, turning into sulphuric acid and falling back to the face of the earth and scalding the life out of vast regions of our planet. It was a very serious problem for a while. Once people realised the nature of that problem, of course, they started to act to deal with it. Some governments brought in rules that people had to burn lower sulphur content fuels. Other governments mandated the placement of scrubbers on smokestacks to scrub the sulphur out of the flue gas before it got into the atmosphere. And a very, very smart man, a man called Richard Sandor, realised that if you allowed people to trade in the right to pollute, in other words, you licensed them to pollute, charged them something and allowed them to trade in that right to pollute, you could deal with the problem very cost effectively. He set up something called the Chicago Sulphur Exchange, which dealt with that problem extremely cost effectively. And that basic concept, dealing with sulphur, is really the foundation stone of all of the sort of carbon trading schemes you see in the world today. It was the beginning of Australia's own carbon trading scheme that we'll see in 2 years' time. As a result of all of that activity, by the mid-1980s, acid rain was really a receding nightmare. And you know, when I think about it, those thousands of kilometres of damaged forests and soils and lakes, it is just astonishing to me that nature repaired itself, that our Earth system repaired itself. You know, I suppose we're all used to our own bodies repairing themselves because we're a pretty well-integrated series of cells, a single organism. And you can understand that our bodies would repair themselves following damage. But for the Earth system, for the living Earth to repair itself on that sort of scale, is to me nothing short of a miracle. It's an astonishing thing that we just take for granted every day of our lives. We can inflict damage on the ecosystem and it will repair itself. And we never give sufficient thought, it seems to me, on that miraculous process, and never try to understand it sufficiently and understand which sorts of damage are particularly dangerous to our planet and which are not. The second air pollution crisis that I've experienced was very different from the acid rain problem. After all, once we got the sulphur out of the air, the world started to repair itself very quickly. The second problem really became widely understood in the 1980s, and it became known as the hole in the ozone layer. I don't know whether you remember, but right across the Antarctic every spring, ozone started to become depleted, and this hole in the ozone layer was spreading out every spring across Australia's southern capitals and other southern parts of the world. This was an astonishing, I think, astonishing pollution problem. No one initially knew what was causing this. We had no idea whether it was a natural phenomenon or was caused by man-made pollution or whatever. And three chemists, Nobel laureates, or got the Nobel Prize for this work, actually understood what was going on by about the early 1980s. What they discovered was that a particular chemical that didn't exist in nature, that humans had manufactured but didn't exist in nature, was the cause of the problem. That chemical was a thing called chlorofluorocarbons, family of chemicals that were being used for a whole lot of industrial purposes from the 1930s onwards. They were used in refrigeration, for blowing up styrofoam cups, as propellants in those little spray cans and so forth. And there was a couple of reasons why this work was looked on sceptically, or these chemicals were, people didn't believe they were the cause of the hole in the ozone layer. One reason was that they were just unbelievably rare in the atmosphere. It took that great genius James Lovelock to invent a machine that could even detect them at the few parts per billion that they were present in the atmosphere. The second was that chemists had been hailing these chemicals as the environment's friend for many years. The reason they've been doing that was that CFCs don't seem to interact with anything at the surface of our planet. And of course, chemicals that don't interact with anything are not going to be causing a problem. What these three chemists that won the Nobel Prize realised, however, was that once the CFCs wafted up in the atmosphere to the ozone layer, which is about 25 kilometres above our head, they started to break down, and the chlorine in those CFCs was released, and a single chlorine atom from that source could destroy many thousands of ozone molecules. This realisation galvanised people because these chemicals are long-lived in the atmosphere. They can last up to 50 years. And the ozone layer, of course, is critical to life on Earth. In Victoria, if you go out on a sunny summer's day without a hat on and without any sun protection, you're likely to get sunburn in about 20 minutes. In the absence of ozone, you'd get that same amount of sunburn in a matter of seconds, 10, 20 seconds. Yeah? The ozone layer is Earth's sunscreen. It filters out all of that dangerous, or most of that dangerous radiation, and protects us. So the destruction of the ozone layer was of great concern. And of course, it wasn't just sunburn that we could have suffered. Rates of blindness go up by about 1% for every percent decline or every percent increase, in ultraviolet radiation. Crops fail to germinate because ultraviolet radiation kills the seeds. The oceanic ecosystem's affected because plankton in the surface levels of the ocean are killed by all of that additional UV radiation. With all of that at stake, the nations of the Earth got together on the 16th of October 1987 in Montreal, Canada, and decided to ban these dangerous chemicals. And it was a great moment for humanity because now, 21 years on, we can see truly what was at stake. If the people of the Earth had not been able to cooperate to ban CFCs and their production in 1987, we have a fair idea of what the state of our planet would be today. When we know that because we know the standing stock of the pollutant in the atmosphere, we know the trajectory of production of new chemical, and we can estimate the impact on the ozone layer. If the Montreal Protocol had failed, we would have been faced with a situation today where there would be a permanent ozone hole over the southern hemisphere, another one over the northern hemisphere, and very significant ozone depletion down to middle latitudes. And that really adds up to a crisis of life on Earth. I don't think that we'd be sitting here in this auditorium today if the Montreal Protocol had failed to come to agreement. And furthermore, I think one day we as humanity will realise the significance of that day, 16th of October 1987, and I'm sure it will be viewed as a great international holiday one day. We have Anzac Day, the Americans have Martin Luther King Day, everyone has their special day, but there's one day that could be humanity's day of celebration, the day we first managed to work together as a species for the first time ever to preserve ourselves from an imminent environmental threat. And that is Montreal Protocol Day. Perhaps one day will be seen as such. In the year that treaty was signed, North America was hit by a series of heat waves, and those heat waves were really were the source of some inquiry and concern. US Congress called people to testify as to what was happening, and a very great climate scientist, a man called James Hansen, gave very eloquent testimony in Congress that really awakened people for the first time on the broad scale to a third atmospheric pollution crisis. This one was not caused by an almost vanishingly rare chemical, nor was it caused by a very short-lived pollutant such as sulphur. This particular problem, James Hansen said, sprang from the very wellsprings of our economic success. He explained that when we burn fossil fuels, carbon dioxide is released into the atmosphere. That carbon dioxide accumulates there, it's very long-lived in the atmosphere, and it traps heat. And the heat that it traps ultimately changes our climate system. I won't go through the climate science because there's a lot of it and it's extremely complex, but I do just want to update you on how bad the problem actually is. The principal guidelines that our politicians and economists and others use to try to gauge what our response should be to this climate problem is the work of a group called the Intergovernmental Panel on Climate Change. That group it contains most of the world's experts on climate science, as well as economists and some political representatives and so forth. It's a rather conservative group, but every 5 years it gets together to publish projections on the state of Earth's climate system, effectively. The most important projections that they have developed were made in 2001, and for the first time what they did was, well, not the first time, but they produced some very believable projections on what I would call the key performance indicators of Earth's climate system. So they set about to ask, for example, by 2100, how much is Earth likely to warm as a result of this pollution problem? And of course there's a wide range of possibilities in their projections. At the lower bounds, they said, well, maybe it'll only warm by 1.4 degrees. And that would be of concern to no one. It's a small amount of warming we could all cope with. The upper bounds of their projection, however, suggested that perhaps Earth would warm by as much as 5.8 degrees. And that's just not survivable for our global civilization. That is that would push Earth into a new climate system that would just be alien to the way we live today. Of course, in the middle, they suggested, well, maybe Earth will warm by 2 or 3 degrees by 2100. And it's those middle projections, those median projections, that people like Ross Garnaut and others use to try to gauge what our response should be to that particular problem. What's happened, however, since those 2001 projections were made is that scientists have continued to collect real-world data on things like how much the Earth's warming and some of the other projections that the IPCC looked at, and have compared that with the projections, because they want to know whether what we see in the real world is in fact reflected in those projections of what things might have been like. What they're learning from one area after the other is that changes in the real world are lying either right at the upper edge of the projections or beyond the envelope of projections altogether. So if you look at that at least the early part of those projections, so from 2001 to 2007, you find that they're not very good predictors of how the world's changing at all. They're far too conservative. So what that also tells you is the path we're on at the moment is a very dangerous path. It's towards the upper end of the projection range. The key performance indicators of the climate system that are most telling in this regard are the overall temperature of our planet, increases in the surface temperature of the planet, increases in sea level rise over time, and increases in the amount of carbon dioxide in the atmosphere. For all of those things, we're either right at the upper edge or outside the bounds of the projections. And that is a true danger signal that I think we are yet to fully appreciate the significance of. We've got less time than we thought, the problem's more severe than we thought, and we're just on the wrong trajectory altogether with that. The other area that's, I think, worth having a look at just briefly is what's happening in the Arctic regions. If you look at the North Polar ice cap and the rate that it's melting away, it's just beyond anything the scientists imagined 3, 4, 5 years ago. In 2005, for example, up to that point, up to 2005, the Arctic ice cap was melting away at the rate of about 8% per decade. And at that rate, there would have still been some Arctic ice left by the end of the century, by 2100. 2005, however, saw a very, very rapid increase in the melt rate. The rate of ice loss increased about 4-fold. 2006 was almost as bad, and 2007 was the absolute champion year of ice loss. We lost about half of the ice remaining that year. This year is looking quite serious. Not as bad as 2007, thank heavens, but another year of significant ice loss. We won't know the full extent until the end of the melting season in September. But at the current rates of ice loss, if you just look at it from 2005 onwards, there may be no polar ice cap in as little as 5 or 10 years. And of course that will change the nature of our planet, because once that ice is lost, all of that solar energy that hits the ice will be captured. At the moment what happens is radiation from the sun hits the ice and reflects back into space. 90% of the energy is just reflected back into space and doesn't serve to warm our planet. But with the ice melted and a dark ocean revealed underneath, 90% of that energy will be captured and turned into heat energy. And the sun, sends down about 240 watts worth of energy per square metre on that northern ocean. That is a vast amount of energy that, once the ice is melted, will start heating the surface levels of the Arctic Ocean and changing the climatic gradient right across the northern hemisphere, the gradient from the pole to the equator. And also, of course, will put more pressure on the Greenland ice cap, which is already melting. So, for the key performance indicators of the climate system, things are not looking good. Earlier this year, in late March, James Hansen, the man who first really alerted the world to this problem, and 8 colleagues published a scientific paper trying to summarise what all of this meant. They went back to the basic work done by the IPCC and re-examined the underlying assumptions that were used to build those projections, and came up with a very, I think, informative view of climate science. What they suggested was that if you take a slightly longer term view than the IPCC does in their century-long projections, the atmosphere is about twice as sensitive to a given amount of greenhouse gas pollution as the IPCC assumed. So instead of a 3-degree rise in temperature for, say, a doubling of carbon dioxide in the atmosphere, we're likely to see a 6-degree rise in temperature. And that's very consistent, I think, this new work, with what we actually see in the real world in terms of these key performance indicators of the climate system, certainly with what we see in the Arctic. They then asked a very fundamental question, which is, well, what do we do about this? What does it mean in terms of our lives and how we live it? And they framed that question around 2 particular points in time. They said, there clearly in Earth's climate system is a tipping point, a point where the burden of pollution builds up so much that it can potentially cause dangerous change. They said, and because the climate system has a lot of lags in it, it takes time for the heat to be distributed in the oceans and so forth. There is also a point of no return for the climate system. And at that point, no matter what we do, we won't affect the system. It then has its own inertia and trajectory. In terms of their understanding of the potency of this pollution to change the world, they made the point that we are already past the tipping point. There's already enough pollution in the atmosphere to cause irreversible damage to the atmosphere. But it's likely to take 2, 3 or maybe 4 decades for that pollution to cause enough heat to be distributed through the system that we would pass the point of no return. So at the moment we are somewhere between that tipping point and the point of no return. And that means that we need to act very quickly to deal with this problem, because once we hit the point of no return, all of the carbon trading in the world and all of the regulation we do will have no impact. It's simply the system is beyond human reach to influence. They set about saying, okay, given that understanding, what do we actually need to do? They tried to do some computer modelling, for example, on whether if we stop burning oil by 2030, that will be a big enough impact. The answer was no. We just don't get enough carbon out of the air by doing that. What about oil and natural gas if we stop burning both of those by 2030? Again, the answer is no. Just you don't get enough bang for the buck. You don't get enough carbon savings. The one thing that they looked at that could give us sufficient reduction in emissions is by stopping burning coal in a conventional manner by 2030. Think about what that means. It's already 2008, yeah? So what that means is that within the next 22 years, we have to either decommission or retrofit with carbon capture and storage every coal-fired power plant on the planet. Yeah? And compare that scientific assessment of what's required with political action. You know? People in Australia are talking about, well, the federal government's committed $500 million to developing carbon capture and storage, but we're not going to have, you know, a plant up and running presumably till 2012 or 2015, and that'll be a single demonstration plant. By then we've only got, 15 years to go before we've got to decommission all the world's coal-fired power plants. The coal industry itself is making more money than it's ever made. You know, the price of thermal coal has doubled in the last 12 months. The price of coking coal has more than tripled. And yet the investments that the industry itself is making in this are trivial by comparison and clearly insufficient to meet the sort of goals that the natural system is imposing on us. I'd argue that of all of the technologies that we look at to save us in future, whether they be geothermal energy, wind, solar, clean coal, nuclear, whatever you want, there's only one non-negotiable technology, and that is clean coal. It's the one that we absolutely have to have, and have to have in very, very short order. And that's because if you look around the world, people are not going to walk away from the assets that those coal-fired power plants represent. China has just gone through a process of building 800,000 megawatts of brand new coal-fired plant capacity. Yeah, that's like 800 Yalawns. It's a lot of power capacity in those stations. It's all new. They're not going to walk away from it. It's going to have to be retrofitted, and retrofitted extremely quickly if we're to avoid passing that point of no return. I don't think that the clean coal technologies are going to be safe. I think they're actually going to be quite dangerous, and I think people are going to have to live with that danger. I don't think they're going to be cheap. I think they'll push the price of electricity far beyond that would be required if we had a clean slate and were able to go to wind and solar and everything else. So it's going to be it's going to be dangerous, it's going to be expensive, but we have no choice. And it's also morally invidious, because those people in the coal industry are clearly unwilling to spend the money that's needed to secure their own future. They're going to expect governments to give them money, and we already see that with this current carbon trading scheme, give money to the very people who lied to us for decades and got us in this problem to begin with. The US coal industry and a few others have spent something like $60 million through the 90s misleading people on the nature of this problem. So we're giving money to the people who put us into this problem to begin with. But again, we simply, in my view, have no choice. It's not moral, it's not safe, it's not cheap, but it is essential. So that's my sense of where we need to go with that clean coal technology. I'd like to just turn now, my time's run out almost, goodness, to a couple of other key areas of hope. It is a fact of our planet that 8% of the atmospheric carbon dioxide is drawn out of the system every year by plants. Yeah? And that means that if there was no carbon going into the atmosphere, within 12 years there would be no atmospheric carbon dioxide. We have, in the natural systems that surround us, these trees and whatever, enormously powerful engines for dealing with this problem. What we need to do is change the way we relate to all of that living planet of ours in a way that that alters the carbon balance from a negative one to a positive one. And I have time just to look at two areas that we can, that I think are critical to doing this in. One is the world's tropical rainforests. You know, they are being cleared at such a rate at the moment that about 18% of all of the carbon dioxide going into the atmosphere is going in from the destruction of tropical rainforests. But the tropical rainforests are much more important than just from a carbon sense. They only cover a couple of percent of the surface of our planet, but they're home to about, I don't know, half of the world's, or at least the land's, biodiversity. They're also hugely important to the climate system because the transpiration that they produce helps cool our Earth. If we could just go some way towards stopping the destruction of the tropical rainforest, we will have done a wonderful thing. And of course, to do that is going to take a very different approach to the one that we have at the moment. I worked in Papua New Guinea and eastern Indonesia for 20 years. I know about the village people that live in those areas and know about the nature of government in those regions. The government is, in those developing countries, often corrupt, self-interested, and money that flows to government very rarely gets down to the village level. If we're going to save those tropical forests, we need to open a dialogue directly with the poorest people on our planet, the tropical farmers of the undeveloped world. And we have the means of doing that. If we could just get a computer into the local village and could, through NGOs and so forth, get the village to put a bit of a blog up in the blogosphere, or I'm no expert on this, but young people here know what I'm talking about, of their land. You know, so they could say, well, here we are, we're Village X, we want to replant this area of degraded forest, or we want to protect this area of forest. Can someone pay us to do that? And if you had an auction system, like an eBay-based auction system, to get money directly to the village level for those improvements, and of course to secure our climatic future, we will have done a great thing, because we're dealing there with the engine of the Earth system, the most effective engine of the Earth system we have for drawing down carbon. And we could start, I think, drawing carbon down at the gigaton level, which is what's required. And, you know, the burden of the pollution in the atmosphere at the moment is about 200 gigatons of carbon. If you can draw down a couple of gigatons a year from tropical reforestation, you're going a long way towards healing the problem. The other area that's critically important is agriculture. It's, you know, when you look at our agricultural systems, they are where we interface most intimately, at least in Australia, with the carbon cycle. We draw a hell of a lot of carbon out of the atmosphere each year into our agricultural systems. And we also, unfortunately, emit quite a lot of greenhouse gas from agriculture into the atmosphere. And I'd like to, in my last 2 minutes, take those two thoughts and just give you two simple examples. We can follow up with questions later perhaps. But, you know, in New Zealand, they ratified the Kyoto Protocol. They decided to count agriculture out of their carbon accounting, and they ended up with $1 billion liability under the Kyoto Protocol, and New Zealand has to pay for that. It turns out that a single intervention in a single agricultural sector in New Zealand could have obviated that debt, could have done away with that debt. And that deals with the dairying sector in New Zealand, and with nitrous oxide, one of the greenhouse gases, the third most important of the greenhouse gases. It turns out that applying what are called nitrification inhibitors to dairy pasture in New Zealand can be done at the cost of around $120 a tonne. The average cost of nitrogenous fertilisers on those same pastures is on the order of $140, sorry, not a tonne, per hectare. So it's about $140 per hectare. So dairy farmers in New Zealand could save themselves $20 a hectare by putting nitrification inhibitors on their pasture. And I should just explain to you what these inhibitors do is make sure that the nitrogen in cattle urine and whatever stays around in the soil longer for plants to use and doesn't turn into nitrous oxide and escape to the atmosphere. We already use them when you use pelletised fertilisers. They're all pelletised with these inhibitors on them. So that simple application that would save you $20 a hectare could, by preventing the release of nitrous oxide, save New Zealand an additional $1 billion under the Kyoto carbon trading scheme. And if there's any farmers in the room here, I just say to you, don't be scared of carbon accounting under a greenhouse system. You will be the great winners in this system. Those sort of examples give me faith that if we look even at the most intensive of farm utilisation, whether it be feedlotting or whatever, you'll find yourselves on the right side of the balance sheet. in the longer term. Broadacre agriculture, of course, offers even more opportunities. I can see a day coming one day when a farmer will grow a paddock full of wheat, and instead of just harvesting the wheat and selling the grain part of it off, they'll harvest the whole plant, and they'll have what's called a pyrolysis machine being dragged along behind the trailer. A very simple machine, just a charcoal making machine. And that machine will generate synthetic gas that will be driving the tractor and perhaps putting some more into storage to run some electricity down the line. And at the other end of the machine, you'll just get charcoal, and it'll be just ploughing the charcoal back into the field. And that charcoal is miraculous stuff. I mean, you know, you and I and wheat plants and any other biomass around the place, we're all volatile carbon. The moment that we die, we start returning to the atmosphere very quickly. All the carbon in us starts going back as we rot into the atmosphere. But I know as a paleontologist that doesn't happen with charcoal. I've used charcoal all of my life to do carbon-14 dating. I've picked bits of charcoal out of soils that are thousands of years old. Hasn't rotted away. And charcoal is pure carbon. So if you're looking for a mechanism in a carbon trading scheme that allows you to sequester carbon very effectively, there's nothing better than charcoal. It's safer than carbon capture and storage. You can do it on a gigaton scale, it can be huge, and it benefits the soils. Charcoal is great if you've got acid soils. It helps to reduce acidity. It's got residual minerals and nutrients in it. And it also, because of its cellular nature, acts as a bit of a sort of the equivalent of a coral reef in the soil. It's a home for microbes and mycorrhizal fungi and so forth. It helps plants to grow. So in future, the farmer with his tractor and his charcoal making machine is going to get 4 crops out of that one piece of land. He's going to sell his wheat, as he always has. He's going to be saving on fuel costs because the pyrolysis machine will be driving his tractor and his electricity back at home. He's going to be paid for the carbon he sequesters in the field. It's his 3rd crop. And next year he's going to get a better crop than he got the year before because of the amelioration of soil that the charcoal will carry out. And of course, at the same time, we'll be saving the world. There's a paper recently published in the journal Nature that suggests that we could be sequestering 9 gigatons of carbon per annum out of the atmosphere using pyrolysis machines globally by 2030. That's 5% of the standing stock of the pollution we could be pulling out per year by 2030. But of course, none of this is going to happen until we have a price for carbon. Until we have a carbon trading scheme and people are required to pay for their pollution, the upfront costs of those pyrolysis machines are going to remain an obstacle to their broad-scale uptake. I think I've finished just on time. I can see the Mayor coming up to pull me off the stage. So thank you very much for listening.
Thank you very much.